Hello. Mic is on this time. Good, so we are reviewing a little bit what happened yesterday and then keep going. The goal is to prove the following. I think I called it the theorem. If we take gamma equals PSL2Z, which is the group of all A, B, C, D in mat 2 to Z, so the A, B, C, D are integers, determinant is equal to 1, and we consider all of that mod plus minus the identity, that's the P in front, then this is a lattice in PSL2R, which is the same thing as up there, where you put instead of the C here an R. Moreover, and that also explains a bit this notion, moreover, the following triangle it's a hyperbolic triangle, is, we can probably make it all the way precise, is a fundamental domain. And I draw it. So I need 3 geodesics to draw a triangle. And I draw the triangle by using the geodesic connecting the point at the boundary -1, the point at the boundary 1. So this is a geodesic, a half circle in Euclidean sense, but geodesic in Euclidean sense, in a hyperbolic sense. And I then draw vertical geodesics at -1/2 and at 1/2. And then I get a hyperbolic triangle in between, enclosed by these 3 lines. It stretches off all the way to infinity, so its diameter is infinite. But as we will prove, it has finite hyperbolic area. And this finiteness of the hyperbolic area is what's important for us, and that makes this subgroup a lattice inside PSL2R. We'll see it again more precisely. And what is a fundamental domain? That question also came up yesterday. Definition, E in H is a fundamental domain. If gamma applied by Möbius transformation to any point in the hyperbolic plane, intersection with E consists of 1 point for all Z in the hyperbolic plane. So if you're trying to understand the quotient H2 mod gamma, and you have such a fundamental domain, you could just, in some sense, just say my quotient is precisely this fundamental domain. Of course, potentially with a different topology, different geometry than when we think of this as a subset of H. But we have seen this before. You understand this in the case of a torus. We drew always a square and said the left is glued to the right, the top is glued to the bottom. And I don't think you had a big problem with that. Nobody complained much about this. And if you want to make it a very strict fundamental domain in this sense of this definition, where you then take here an R2 and here take C2, acting by translation, then you would say, okay, I include the boundary on the left, but not on the right. I include the boundary at the bottom, but not at the top. Et voila, then you have a fundamental domain for the torus quotient. And the same thing we could do here. We could say, I include the boundary on the left, but not on the right. So I make it a dashed line to indicate that this dashed line does not belong to the set E that we are thinking about. And similarly here, this is glued to itself by gluing this part to that part, so that dot should be contained, but this half line segment would be identified with this half line segment. So don't include it in the set, make it open here, but closed here, and then everything is okay. Okay. Yeah, we need to come back to this lattice, but maybe let's talk about this, why this is a fundamental domain. I drew this last time. Let me draw it again. The gluing that goes from the left side to the right side is Z goes to Z plus 1, corresponding to one, 1, 0, 1. If you let this matrix in PSL2Z act on the hyperbolic plane by Möbius transformations, it will shift everything to the right, and it will glue the left boundary here to the right boundary here. And there is another important matrix that glues the left half of the third side to the right half of the third side, which is Z goes to minus 1 over Z, and this corresponds to the off-diagonal matrix 0, minus 1, 1, 0 in PSL2Z. Okay? There is a question. I also asked you to come up with questions in case we want something on record from last time. So if you have any questions concretely from last time, do ask them before the hour is over, and I just keep going with the proof of this for now. We also go back to the, yes, now you have a question.
Maybe one thing about the definition of lattices.
Yeah.
Because we've also defined uniform lattices.
Yeah.
I mean, there was something about the volume that we haven't really defined yet. You said
Yeah. We'll come back to it, yes.
Okay. So, because my question was whether a uniform lattice is also a lattice.
Yes, okay. So we talked a little bit about what a lattice is and what a uniform lattice is last time. We'll do that again. But indeed, a uniform lattice, where the quotient is compact, will always be also a lattice, because something that's compact will have finite volume. That will hopefully be obvious once we understand it a bit better, what these notions are. Yeah, thank you. Let's prove the moreover part for now. That's a concrete statement. Here's the definition. Let's prove that. Prove that the triangle E is a fundamental domain. Let Z in H2 be arbitrary. Right? When we want to show that it's a fundamental domain. We have to take any point whatsoever somewhere. And the first stage is that we want to find a representative within the triangle. So we want to find a gamma so that gamma times Z is in the triangle. We wish to find gamma in PSL2Z so that gamma applied to Z belongs to E. Recall that the imaginary part of gamma, or let me even write ABCD, Möbius applied to Z, is equal to the old imaginary part divided by absolute value CZ plus D, probably squared. It's a concrete calculation that was important already last week. We don't have to repeat the calculation all the time. You can repeat it a few times until you really believe it. I have repeated it already in my life a few times, so I believe it. And that's quite nice, and it's helpful for us because it somehow tells you a bit of the geometry of this cloud of points. Right, when I apply now integer matrices to my given starting point Z, I get a cloud of points in the hyperbolic plane. And how does this cloud of points really look like? What can I say about this cloud of points given this formula? Somewhere is my original point. I don't know. Maybe this is my original point. Maybe this is my original point. And then this PSL2Z will create other points. Like if you have a point, you can always add or subtract integers left and right, and you get more points on the same height. But it's kind of difficult to get more points higher up, or to get points that are really, really high up. Why is that? Because Z is in the hyperbolic plane, which means it's a complex number. It has positive imaginary part, which means that this number and 1 are linearly independent over R. And CD are integers, so they're in particular the real numbers. So this quantity, unless C and D are simultaneously 0, this quantity will never be 0. C and D cannot be simultaneously 0 because they are from a group element, right? So this denominator is never 0, and this denominator tends to grow rather than to be small because C and D are integers. So this quantity can never be small, which means this quotient can never be big, super big. Or said differently, because of the discreteness of the C and D, there's a maximum value for this. Because Z contains an imaginary coordinate. Okay? As the imaginary part of Z is positive, and CD are integers that are not both 0, the imaginary part A of gamma Z for gamma in PSL2Z obtains a maximum. I don't want to write this down sort of in pure logic, but I want to explain again why this is true. if C gets large, then the imaginary part of C times Z plus D will be the imaginary part of the Z multiplied by C and will be large. So the norm will be large and the imaginary part of the quantity will be small. Also, if D is getting large, but C is like 5 bounded, but D is large, then the real part of that will be quite large, namely almost as large as D. And again, this quantity will converge to 0 and not be large. So to have hence you get a maximum of this quantity. So there is a representative in the orbit that is highest up, like this guy. Maybe this is what we started with, but then we found an ABCD so that we get to the maximum value. But that guy might not be in E. So what do we need to do? We need to add or subtract an integer, but we know how to do that because we have this matrix. So we can apply to the best first guy another shift by an integer, and then we will be able to move into E. Which we will see, which we will have to show. Let maximum, say, achieved at gamma 0 applied to Z. We apply 1 N1 to gamma 0 applied to Z and can achieve that 1 N1 gamma 0, and maybe this is our gamma 1 now, applied to Z has real part in minus 1/2, 1/2. That's easy, right? We just shift left, right until we have the real part between minus 1/2 and 1/2. What we don't yet know is what the norm of this guy is. The claim is that the norm of that guy is now still bigger than 1. And that would be the definition of E. Claim, let's call, we called it gamma 1Z. Claim gamma 1 applied to Z. Complex norm, so that's just the complex norm, is greater or equal 1. i.e., gamma 1 applied to Z belongs to E, belongs to our triangle. Because E is precisely the region of complex numbers between the vertical lines at minus 1/2 and at 1/2, consisting of everything that has norm bigger or equal than 1. That's E, right? So if we have this in addition to what I say here, then we are in E. I'm ignoring the boundary again. If you're on the circle, you might have to flip to be in the right part of the circle, meaning the left one here. Okay. Why is that true? Well, if it's not true, we get a contradiction. Because if gamma 1 applied to Z has norm less than 1, then the imaginary part of I'll explain it in writing, in a picture, but it doesn't quite follow from this formula up there even for, yeah, it should, but it doesn't quite. Then imaginary part of, I apply the other guy, the blue guy here, after the gamma 1, 0 minus 1, 1, 0, gamma 1, Z. This imaginary part will be bigger than the imaginary part of gamma 1 Z, contradicting our choice of gamma 0. Nobody said that gamma 0 is unique, right? But gamma 0 maximizes the imaginary part in the orbit. And if I can apply to the gamma 1 this integer matrix on the left and the imaginary part gets bigger, then my gamma 0 was wrong. And see picture. We are doing a bit of geometry here, right? So it's okay to occasionally draw a picture. We are now in the unit circle because we are assuming the opposite. So we have a point inside the unit circle, inside this strip between minus 1/2 and 1/2. So it's somewhere here. And we are doing minus 1 over Z. That's basically inversion on the unit circle, right? So 1 over Z, the inversion on the unit circle is not holomorphic, it's anti-holomorphic. But 1 over Z is doing a flip along the x-axis and an inversion on the unit circle. And then we're putting in minus in front so that we are again on the upper half plane. So what I'm trying to say is that this point will be mapped to this point. And you notice that it's higher up than this guy, which is what I claimed here. Inversion on the unit circle will make a number that's inside the unit circle bigger. And the ratio between real and the imaginary part stays the same. So forgetting the absolute value of the ratio. Hence, the imaginary part will actually grow. Okay, so that achieves half of what I claimed. Namely, it achieves that the intersection of gamma, capital gamma, Möbius applied to Z, intersected with E, is at least 1 point. In fundamental domain requirement, we wanted also more. We wanted at most 1 point. So now we need to we need to consider 2 points inside E on the same orbit and ask if that's possible, if they're really 2 different points. And if it appears, then it should only appear at the boundaries. And if I define my E correctly using the dashed lines as I did, then it shouldn't be possible. Okay. To finish the proof, we assume Z is in E, gamma Z is in E, and without loss of generality, I'll keep it as it is here. Without loss of generality, I want to assume that the imaginary part of the second guy is bigger or equal than the imaginary part of the first guy. Imaginary part of gamma Z is bigger or equal than the imaginary part of Z. of course, for gamma in PSL2Z. So we again look at the formula up there. This is a very useful formula, so we can use it many times. And the gamma is ABCD again. And the imaginary part of gamma Z is bigger, right? So that means by the blue formula above, this means that CZ plus D must be less or equal than 1, right? Because the gamma Z has bigger imaginary part. How can it get bigger? It can only get bigger if the denominator is less or equal than 1. Okay? Z is outside the unit circle, right? Because Z is in our triangle. Z is in E. Z is outside the unit circle. That means its imaginary part is at least square root 3 over 2. Where did square root 3 over 2 come from? It's from the lowest part of the ZE here. So here we have a square root 3 over 2 thing. The imaginary part is at least square root 3 over 2, which in particular is bigger than 1/2. If C is 2 or more, if this C is 2 or more, then the imaginary part of that will be 1 or more, which will make this very difficult. The imaginary part is strictly bigger than 1/2. If C is in absolute value bigger or equal than 2, this is impossible. So using Z is in E, this forces C equals 0 or plus minus 1. No other choice. If C is equal to 0, D is equal to 1 without loss of generality. Why? Because the absolute value is then less or equal than 1, right? And minus 1 doesn't count because minus 1 is equivalent to plus 1. We are doing everything mod plus minus the identity, and I can, But if then I know pretty much of this matrix here, I know the total last row of the matrix, 0, 1, then the A needs to be 1, because we want the determinant to be 1, and B needs to be an integer. One, B, 0, 1 is our gamma. Okay. And now we know what the gamma is really doing. It's just shifting by B. So we have Z is in E, and gamma Z is in E, and the gamma is just shifting by an integer. And now we are talking about this boundary issue, and if our E was correctly defined that the right boundary is not there, then we can't even shift by 1. Then we can only shift by nothing. So then B is equal to 0. Using Z, gamma Z in E, this implies gamma is the plus minus the identity. That was the case c equals 0. Now we treat the case c equals 1. Again, -1 doesn't matter because one sign I can always fix. If c is equal to +1, I look at this up here. I have now, this simplifies now. Then absolute value of z plus an integer is less or equal than 1. And now I ask myself, how often does this happen when I have an element in the fundamental, in this triangle E? I shift it by an integer, and the output is still inside the, on or inside the unit circle. How often does this happen? So I draw a shifted picture of this E. I can shift it over here. How many points here are still inside the closed unit circle? Well, there's this guy, which corresponds to that guy. And I can shift to the right instead. How many points, again, do I have from the shifted region that are still inside the unit circle? Well, there's this guy, which is the same guy again. So what I'm trying to say is if c is equal plus 1 and z plus d is less or equal than 1, then d is equal to 0, and we are back to the previous something similar to the previous discussion. No, not quite. D is equal to 0. C picture. If we do shift, then we are just talking about one point, namely this point in this corner point, and the shifted guy will not be in the it's a different shift, but it's still true. This is not the Möbius transformation. This is just a formula that popped up somehow. Right? This is the formula that popped up in the denominator of the imaginary part. If c is 1, the c equals 0 case we understand. If c is 1, then this formula coming from the blue box simplifies to z plus d is less or equal than 1. Z is from this triangle, and I shift it left, right, maybe by more. If I shift it by more than 1, it will never touch the unit circle. So I need to shift it by 1. And then potentially only one point will, inside E, will still satisfy this formula. So maybe I should talk about that. If D is not equal to 0, then Z must be the third rule of unity. Okay? This is now C picture, because all other points inside the triangle will not satisfy this inequality if D is equal to 1. Okay, so that would mean that we have, in this case, we have our gamma is the C is equal to 1, and the D is, which direction did we shift? What was the D precisely? We said our third root of unity point is in E, and this we can add 1 to it, and then we are still inside the closed unit circle. If you subtract one or a larger number or add a larger number, we are not anymore in the unit circle. So gamma will be of this form AB11. The determinant is 1, right? So that means B minus A is 1. B minus A is 1. We are anyway already just talking about this 1 point. And if we gamma is AB. A minus B is 1. A minus B is 1. So A plus 1, no. A minus 1. A, yeah. So because the determinant is 1 and I know the bottom row, I know I can reduce this now to just one amount of freedom. And it's A is an integer and A minus 1 must be the top row. And I could ask myself now what this is doing when I apply it to the Möbius when I apply it to my third root of unity and figure out where I land. I'm sure this has a different what would need to be here so that I get this. -1. Minus A. Zero, 1. No, I don't want to. I think I don't want to keep going in this rabbit hole. Exercise. This subcase is an exercise, and what's remaining for us to do if D is not equal to 0, if D is equal to 0, so C is plus 1, and D is equal to 0, it's not rocket science. It's a few subcases to be dealt with. And I make it more complicated than it's supposed to be. Let's look at it again. We have Z and gamma Z, they're both inside E in our triangle. And there's symmetry between the two. We can always take the inverse of gamma if we want to. We may assume that the imaginary part of gamma Z is at least as big as the imaginary part of Z, and gamma is ABCD. By the formula for the imaginary part, this means that CZ plus D is less or equal than 1. If Z is in E, and if the C would be larger than, would be 2 or larger in absolute value, then the CZ plus D will never be less or equal than 1. Wouldn't be true. So we only have to consider two cases. If C is equal to 0, then again by the inequality for CZ plus D, D must be 1 without loss of generality, and then we know gamma pretty much completely. And then we know that, yeah, that we are just shifting left and right, and our triangle was half open, defined correctly, so that the gamma actually cannot move a point from E back to E. Not even the boundary point is mapped back to E because the right boundary we removed. So that means we are down to the case C is equal to +1, in which case our formula up there, CZ plus D is less or equal to 1, simplifies to Z plus D is less or equal than 1. If D is not 0, then this actually implies that Z is only the third root of unity point, and we leave this as an exercise. So now we are considering the case when D is equal to 0. Now suppose finally D is equal to 0 and C is +1, so that gamma is equal to, we know the C, which is 1, and we know the D, which is 0, and then we have an A and a B, except that the B we now also know, the B needs to be -1, because otherwise the determinant would be incorrect. Okay? And again, everything is about matrix multiplication, but on which side do I want to do this? I want to take this guy and say this has something to do with a shift and a flip, I think. No, maybe again this is something else. Said. Right, so, sorry. There's something else that we know, and absolute value C is less or equal than 1. So we're again just talking about stuff at the lower boundary part. And if you are happy to ignore null sets, and sooner or later we're doing ergodic theory and we're very happy to ignore null sets, then we are already done anyway. If you are not happy about that, then you need to go and dig into this expression again a bit more and analyze how can this gamma, which looks like this, take a part of the circle and move it again back into a part of the circle, and then you will get the more constraints on the A again. But I also leave this an exercise because I'm not as tired as yesterday, but I'm still tired. So. Good. So that, let's say, ignoring the boundaries a bit, tells us everything we wanted to know. For any point whatsoever on the hyperbolic plane, we can find an integer matrix so that this integer matrix will move our point into the triangle. And if we have 2 points on the triangle that are on the same orbit, then the only way this can possibly pop up is when the 2 points are both on the boundary. And if we are careful with the boundaries and do this exercise a bit more carefully, we will even rule that out and know that this triangle is really a concrete, perfect, fundamental domain. But I'll keep going in this direction by ignoring boundaries and null sets. Yeah, but we need to talk about the measure. We do this after the break. Okay. So let's talk about the lattice part here. And to talk about this lattice part, need to check. Green, light, very good. To talk about this lattice part, I need to talk about the hyperbolic area and then about the H measure on SL2R or PSL2R. So the hyperbolic area A defined by the volume form. It's a measure, and it's even a measure absolutely continuous with respect to the back measure, restricted to the upper half plane. It's defined by dx dy, so I'm just applying Fubini in xy coordinate, but before I finally integrate, I need to divide by y squared. Is preserved by Möbius transformation. If you do have Riemannian geometry, then this is not a surprise. It's somehow, this comes naturally from the hyperbolic metric. The hyperbolic metric is preserved, and hence the volume form defined by it has no other choice than to also be preserved under the Möbius transformations. But let's not talk about that. Let's just show that it's clear by concrete calculation. Let f be a continuous function of compact support on the hyperbolic plane. Let G be in PSL2R. We calculate what it amounts to when we compose f with G and integrate with respect to the dA, and whether the G is really important when we do this composition with G. So integral over the hyperbolic plane, f composed with G, f is my function, G is my group element, dA is equal to integral f composed with G at all points Z in the hyperbolic plane. And then what is the dA? The dA is, Z. Z is obviously x plus iy, and I'm integrating dx, dy, but I'm integrating here over with this 1 over y squared. Or let me write imaginary part of z squared, which it is, right? With the understanding that z is x plus iy. What I would like to have is this composed with G also in here. So we use the formula that we already understand and used a zillion times one more time. That's blue box from just before. So the imaginary part of GZ square, is equal to the imaginary part of Z, CZ plus D absolute value squared, and I square the whole thing just because I like to do that, and I get this formula. So if I now take this imaginary Z and put it here, I can rewrite this in a different way. Integral h squared, f composed with G, and then I have the 1 over the imaginary part of GZ, absolute value squared, and I think I get a 1 over CZ plus D. Yeah, it looks good. To the absolute value to the 4th power, dx dy. Right, I multiply by this and then take this and put it here, and I get this expression. Wouldn't it be nice if this were my Jacobian for the substitution. Well, it is. And hence you can do the substitution, get rid of the G, and you're done. So let's, I'll write it here, and then let's think about why this is the Jacobian. This is integral f, and then 1 over imaginary part of my new z prime, maybe, after the substitution, absolute value squared, which is the function that I see here. This is of z prime, and this is dx prime, dy prime. And the claim is that this lila expression here is the Jacobian. Because 1 over cz plus d absolute value to the fourth is the Jacobian of z prime is equal to g applied to z. Indeed, g applied to z is differentiable. Right? We agreed on that. When we used it as differentiable before, we even said it's complex differentiable. Right? Even as in complex analysis. With derivative. What was the derivative? It was 1 over cz plus d. The complex derivative was 1 over cz plus d parenthesis squared. Right? That was the complex derivative. Parenthesis, not absolute value. So we have a bit of a translation to do. Here we have the complex derivative. But of course, the Jacobian is in the sense of real analysis. So we need to think of a complex differentiable map as a real differentiable map and figure out the determinant, absolute value of its determinant. But that's like saying we have a complex, we have the multiplication by complex number, this complex number, and we want its matrix representation. And then, of this matrix representation, we want the absolute value of the determinant. And if you do this, it's a silly exercise in linear algebra. What's the matrix multiplication when you multiply by A plus IB? It's A minus B, B, A. And when you take the determinant of this matrix, you get A squared plus B squared, which happens to be, surprisingly, the absolute value of the complex number squared. So by doing this translation, this is a complex number, and you need to figure out the determinant of the absolute value of the determinant. When you think of this as a linear map on R2, you get precisely 1 over absolute value cz plus d to the fourth power. Doing the translation of C derivative to R derivative in met 2 R and taking the determinant, we get that the Jacobian is indeed 1 over absolute value cz plus d to the 4th power. And that's what we wanted to know. We wanted to know that the volume measure is preserved, and for this it suffices to look at continuous functions of compact support and prove this expression here. Right, this is integral f dA, and you had forgotten the composition with G. Composing with G doesn't change the integral for continuous functions, so it doesn't change the measure. Because the measure is uniquely determined by how it integrates continuous functions. Is good? Okay. Sooner or later, we want to go to the unit tangent bundle, right? This was on H, on the hyperbolic plane, but we also talked about stuff on the unit tangent bundle, because there we actually know what dynamics can do. On the modulus, on the surface, if someone gives me a point on the surface and say, go, I don't know what to do, right? Because I have no motion, I have just a point. But if someone gives me a point on the surface and the direction to go and says, go, then I know what to do. I just follow the arrow as straight as possible, and that's the definition of the geodesic flow. But for that, I need the unit tangent bundle. So friction is switched off. We don't like friction. There's nothing to prove if we have friction, so friction is switched off, and that's why I insist on unit tangent bundle, because it makes it's not interesting to carry around all different speeds when the speeds are not changing. So I insist of one and the same speed, which means I'm talking about the unit tangent bundle. Okay. It would be nice to have a volume form on the unit tangent bundle as well. Because then I can, do stuff on the unit tangent bundle, maybe prove some things with that. And this is what I do. I just add the Lebesgue measure on the circle to it. Because when, recall that the unit tangent bundle is my hyperbolic plane cross the circle, because at every point I attach a circle. The size of the vectors I already know anyway, because they're supposed to have hyperbolic length 1, so there's no information in the size. And all I need to know is an additional angle parameter. We define vol, or now let's just call it M. We define M, a new measure, on T1H by dm is equal to dA d theta, where theta is the coordinate in S1. We claim that M is preserved by the derivative action of Mobius transformations of G in PSL2R. So as above, but now in a bigger space, even for the three-dimensional thing, the volume is preserved. This volume is preserved. For this, we calculated Jacobian. We calculated Jacobian. in the x, y, theta coordinates. Well, really the derivative, the Jacobian will then come out of it, the derivative. So here we have an x and a y and a theta, and then we have x prime and y prime and a theta prime. Right? And up here we have the derivative that we had been talking about before. This guy as a 2 by 2 matrix is supposed to go here. So not talking about that guy because we already understand it. Now I need to know how much the x prime coordinate is influenced by the theta coordinate. Good question. Who can tell me? What's the derivative here? Nobody knows because I didn't bring the chocolate. Okay, understand. 0, thank you. The theta coordinate is not relevant if I want to know the x prime coordinate because the action was already defined on the hyperbolic plane and then we lifted it. We don't need to know the angle to know the position of the Möbius transformation. So here there's 0, 0. There's no dependence whatsoever. Okay? Here, I don't know. I really don't want to calculate it. Also because I don't have to. Because if I have zeros here and I'm only interested in the determinant, then I don't care about these entries, right? And I have zeros here, so I don't care about these. All I care about is this here. What is this here? What should it be if we are claiming that we are preserving the product measure? It should be 1. So the question is, why is it 1? Said differently, when I calculate the angle of the output vector, but I fixed my position, the x and the y, the z is fixed. And I only want to calculate the angle as a function of the input angle. How does this work? What does the Möbius the derivative action do to the vectors? It multiplies by a complex number. How do angles behave when I multiply by a complex number? Angles add up. What's the derivative of addition of 2 angles when I fix one angle and the derivative with respect to the other angle? 1. That's what I wanted. So the Jacobian is now the same Jacobian that we had before, even in free coordinates. So the calculation from before works the same way and gives me the answer. This shows that the Jacobian is the same as before. And I just stop here. Okay, this is pretty cool because it also tells us something about PSL2R, because the unit tangent bundle is isomorphic to PSL2R. We actually found a measure on PSL2R that's invariant under multiplication on the left, because left multiplication corresponds to Möbius transformations on T1H. So we found in concrete coordinates the H measure on PSL2R. If you don't know what the H measure is, just take it as a definition. It's a measure that's invariant under translation on the left. It has, of course, other properties. It should be finite on compact subsets. It should be positive on non-empty open subsets. But all of that is true in our case. there's another definition. There's another feature of Haar measures. They're always unique. Up to scalars. You can take this measure and multiply it by 15, and then you have another Haar measure. Like, what's the Haar measure of R2? It's the Lebesgue measure you always have known, because it's shift invariant, right? That's what the Haar measure is supposed to do. Yeah, you can go and ask yourself what's the most exotic group that you can come up with that's still locally compact, and then try to figure out what's the Haar measure there. You can always find it. It always exists. It's always unique up to a scalar. You need some assumptions on the group. Don't take R with the discrete topology and then ask me what you want to do there. Of course, you can do the counting measure, which is the right thing in that case. But I'm saying there are some limitations of which generality you want to go with. The theorems about existence uniqueness have assumptions, but they're always satisfied in the cases that we're interested in. Okay. Yes, lattice. So we define again what the lattice is and then prove that part of the theorem here. Definition, gamma in PSL2R is a lattice if, and there are two equivalent notions, ways to define it. There exists a fundamental domain in H2 with finite volume. Or there exists a fundamental domain in PSL2R with finite volume. Always using the correct measure that we talked about, namely in the hyperbolic plane. I want to take the hyperbolic area measure of the fundamental domain in H2. And in the case of the second definition, I want to take a fundamental domain in PSL2R, and I want to take the Haar measure, the measure M corresponding to this dAd data in the hyperbolic world. And the circle direction is not adding any information, right? So the circle is integration over a compact part of the space. That one is not creating a problem, so this definition implies that definition. If this area, if you find a fundamental domain that is perfect here in H2, and you attach all vectors to all points in the base, that is in the, to all base points that belong to the fundamental domain in H2, you might not be a fundamental domain, but you would be contained, it would contain a fundamental domain. There's some technical issues there. Concerning 2 points that are always the same 2 points that make trouble. So this guy is creating troubles, and this point is also creating troubles. So if let's quickly talk about what the trouble is that they are creating. If you take a point here, or also a point here, and you look at all vectors attached to it, they are all inequivalent. They cannot be mapped to each other using a gamma. But this guy is kind of special because it's actually fixed under a Möbius transformation, namely under this Möbius transformation. But this Möbius transformation is not fixing the vectors. So that means that this vector is actually mapped to that vector. They're equivalent. Even though the point is not moved, the vector is moved. So if you start with a fundamental domain in the hyperbolic plane, and this fundamental domain contains a silly point like this point, then at this point you would have to remove part of the vectors to again create a fundamental domain. But it's again just a null set, and you can do it, I trust you. And here, it's even worse. There's sort of, there are 3 lattice elements that fix that point, and 2 of them don't fix the directions. So you can also say it differently. If you go around this point and count the angle until your circle closes up, it's 360 degrees. Big surprise, right? But if you go around this point until it closes up, it's pi over 2. It's 180 degrees. And if you go around this point until it closes up, infinitesimally counting, so to speak, it's 120 degrees until it closes up. So these points are called conical points. They have sort of a bit weird behavior. So that means that the quotient of the hyperbolic plane by this lattice is actually not a manifold. It's a manifold with 2 weird points. It's sometimes called free punctured sphere, which is weird. What's the third point, and why is it punctured? Well, the third point is at infinity, and that point is kind of also weird. For instance, because it's at infinity and not there. There are many phrases that go around with this thing. And topologically, it looks very, very simple. It's just a plastic bag. I mean, with one open end that is very thin so that you can't fit anything in. That's how it looks topologically when you take the quotient. But there are 2 weird points, so these 2 are weird points. Okay, I talked about it. Now we prove something, namely we prove that it's a lattice, but there's nothing to prove. So prove that PSL2R is a lattice. We calculate A of E. So that's the integral over E of dx dy over y squared. And we are not interested in really calculating it. Yes? Oh, yeah, that's good. Thank you. Thank you. PSL2Z is a lattice. We'll calculate the hyperbolic area of the hyperbolic triangle, but we are not really interested in calculating it. We are happy to just estimate it, and we get integral from, in the x direction, from -1/2 to 1/2. That's not really bothering us a lot. And the lowest point is this weird point at height square root 3/2. So we just start integrating there, square root 3/2. And we are not really bothered by integrating it. We just need to know that it's finite, and I think we all agree that this is fine. Because there's a definite lower bound, and to the right this is integrable. And the x is just a compact domain, not relevant. Great. Yeah, so yesterday we talked about, we recalled the geodesic flow, and when we said that in this isomorphism, PSL2R is isomorphic to T1H. G is mapped to the derivative action applied to II, the vector pointing north. In this isomorphism, there is a lot of stuff going on. So we can apply here Möbius transformations. And when we do, then on this side, we need to multiply on the left multiplication. And it corresponds. And then we had talked about the geodesic flow. And the geodesic flow is a very concrete geometric thing. We always take a vector, draw the geodesic tangent to that vector, and follow that geodesic for a certain while. That's a very geometric definition. You can write down lots of differential equations that would describe it precisely, or just say it geometrically as I just did. And anyway, define the geodesic flow this way. And that corresponds to right multiplication, but right multiplication by diagonal matrices. Right by diagonal. And then we also talked about another thing you can do. You can just rotate your favorite vector, rotate tangent vectors. Without moving their base point. Without moving base point. And you could do this sort of uniformly across the whole plane at the same speed, etc. And if you do that, that corresponds to right multiplication, but this time right multiplication by the compact subgroup SO2R. P SO2R, because the minus identity doesn't do anything. Okay. And we also had another thing that you can do, like blue, which is precisely this horocycle that we mentioned last time. So let me draw it and then talk a bit more about it. So this is the horocycle flow, a third geometric object that on PSL2R corresponds to right by, let's say, U minus, which are matrices of the form 1S, 0, 1, S in R. And I call this unipotent because the eigenvalues are 1 instead of nilpotent where the eigenvalues are 0. It's a pretty standard terminology. But what does it correspond to over here? And I'll draw the picture again. Here's our reference vector. So to understand all of these correspondences, you always need to study your reference vector. And whenever something becomes true in this correspondence for the reference vector, then it's true. So we only need to understand what multiplication by these unipotent matrices on the right for the identity means geometrically, and if it's a good geometric description, then this good geometric description will stay the same for all other points. If we use right multiplication on the left-hand side of this picture. And the answer is the following. If we take our vector pointing north and we apply this guy, at the identity left and right there's no difference, so I'm actually just applying the Möbius transformation to it. I actually get all other vectors pointing north at the same height, because that's what it does. But the description of the horocycle flow is not translation to the right or something. It's always, I need to translate this into something that has geometric meaning, and then translate this geometric meaning to all the other points. And the geometric meaning is that the horocycle flow creates points that are asymptotic to each other in the future for the geodesic flow. So the geodesic flow had the color yellow. Let me draw it yellow. So here I have a geodesic orbit, and here I have a geodesic orbit, and they move closer and closer together. They're kind of parallel in the Euclidean sense, and at the same distance in the Euclidean sense, but in the hyperbolic sense, their distance goes to 0. So they are asymptotic to each other in the hyperbolic sense. And that's a very nice geometric picture. And if I now apply a Möbius transformation to this and get another vector like this vector, I will get another horocycle orbit that's again, this time a circle. Möbius transformations always map lines or circles to lines or circles. So this line will be mapped to a circle tangential to the boundary. And the vectors will always be pointing inwards and will always have the same limit point. They will be going towards the same limit point at the boundary. Always intersecting here the normal angle, of course. Okay? I think I want to use uniqueness of Haar measures. Sorry. It is a not so difficult statement that the uniqueness is much easier to prove than the existence. The existence in concrete cases, like this case, can be obtained very concretely. There are also some, you can also think of SL2R as a hyperplane in R4, right? It's defined by one equation. So you can think of it as, this is R4, this is some kind of hypersurface. Maybe this is our SL2R, if we could draw it in 4 dimensions. And if you have one way of presenting a group as some hypersurface inside a vector space, then it's actually often quite easy to define the Haar measure. And I'll just give you the picture and then. So you want to define a measure of subsets in SL2R. How could you possibly do this? Knowing that the determinant is 1. How could you possibly do this? You can do this by making the subset into a cone and then taking the 4-dimensional Lebesgue measure of the cone. And if you then play with the definition, you will see that this creates a Haar measure on SL2. Okay, so I have 5 more minutes. I'll tell you what the next goal is, and that needs this tiny little uniqueness fact. And I have like maybe a week plus a bit for this topic left, and I don't want to do things in that 1 week that you will learn in other courses anyway. I would rather give you sort of an idea why this or that is interesting and why you want to learn these things in other courses. Okay, so the next goal is if gamma is a lattice, and we have an example, then there is a nice measure, probability measure, mx on the quotient of PSL2R by gamma that is invariant under PSL2R. And then we get not just one dynamical system, we get even, well, 3 you could say, but okay, 2 is more honest. You get 2 nice dynamical systems to study. Ergodic theoretic systems, measure-preserving dynamical systems. You can study the geodesic flow from a probabilistic point of view, or you can study the horizontal flow from a probabilistic point of view. You can also study the action of SO2, but as I said already yesterday, that's not so interesting. It's a compact group, orbits are all compact. There's not much ergodic theory. It will never act ergodically, so never mind. Okay, and then we can try to answer things like, is this three-dimensional probability measure ergodic under the geodesic flow? Yes, it is. Is it ergodic under the horizontal flow? Yes, it is. Is it mixing under the geodesic flow or the horizontal flow or PSL2R? Yes, it is. Can we say even more? Depends. So what for the geodesic flow, not really. Geodesic flow has, you can say more, namely that the dynamics is very complicated of the geodesic flow. There are periodic orbits around. I can draw you one. Yeah, it looks good, but I don't know whether I really hit the golden mean. So here you should take the golden mean, and yeah. So if you put the golden mean at the right boundary points and draw your circle, you will get a periodic point that goes up here. Now it was wrong, because when it goes up, it actually reaches the biggest imaginary part precisely when it hits this boundary, comes down here, goes back. So it will be a periodic point like this, traversing both things in both directions. But that's just one example. If you like square root 3 better than square root 5, you can find a periodic orbit that goes with that number also. So for any quadratic field, you find infinitely many periodic orbits corresponding to that quadratic field in some sense. Yes?
What is exactly the ergodic system or the dynamical system of the geodesic flow? Is it sort of now from a continuous group into
So
continuous time?
we can consider it continuous time, but you don't have to. We can, for the statement of mixing or ergodicity, it's even through discrete time. So we take time one map, say. Time one map of the geodesic flow that fits into the discrete setting that we talked about, is ergodic, is a mixing. But one can also soften it a bit. The flow, in fact, is mixing. But there's another thing that is really amazing, namely for the horizontal flow, one can completely classify the invariant measures. That's totally not possible for the geodesic flow, but for the horizontal flow, we can completely classify what they are. And there are only two types, this measure, and the other type I can draw. If you have a vector pointing north, and you follow the horizontal flow, it translates. But the Möbius transformation does the same, and you get a periodic orbit. So you have one-dimensional periodic orbits of any length inside the modular surface, and those are the only other invariant and ergodic measures. you get all invariant measures, and then you take convex combinations of these, of course. And there are more statements, and then there are more statements still, and then one can bring in the Riemann hypothesis if one is bored. Okay. Thank you. Have a good weekend.